Well, I'd like to start by thanking the scientific committee for inviting me to come here and speak. And I'd also like to thank the organisers who put on a fantastic conference. And in particular, I'd like to commend them on a very nice website that does everything you'd expect it to do. A surprisingly interesting opening ceremony. And above all, for these fantastic headset microphones, which make me feel like I'm about to go off and fly a helicopter. So, today I'm going to talk about some joint work with a PhD student of mine, Ellie. And I guess my main objective is to give such a good talk that everyone immediately wants to give Ellie a job. So what's the project about? So it's about stone duality. But not ordinary stone duality. Stone duality is something called skew Boolean algebras. So we'll get there sort of about halfway through, I suppose. But I'm going to start by sort of warming us all up by talking about classical stone duality. Okay, so let's get going. So classical stone duality. Okay, so there's actually two forms of classical stone duality, and we'll just sort of go through those. So the first one, as you're probably aware, is concerned with Boolean algebras. So what's a Boolean algebra? I guess we kind of know what Boolean algebras are, but let's make sure we know what they are. I'm going to describe them in a certain way. So they're the complete theory of the operations. So we've got intersection, union, empty set, kind of the whole set, and complement on power set lattices. Okay? So they have those operations, and the axioms that they satisfy are exactly the axioms that hold between those operations in any power set lattice. Okay? So you don't need to know what those axioms are, but I'm going to give you another presentation of them. Okay? So they're also the endomorphism theory of the set 2, which is 0, 1. Okay, so what do I mean by an endomorphism theory? I mean the following, that if I look at the n-ary Boolean operations, so the operations which any Boolean algebra supports, then these correspond bijectively with functions from 2 to the n into 2. Okay? So if you taught a first year discrete maths course, then you'll be very familiar with this fact and discover that the students are rather less familiar with this fact. So that's Boolean algebras. So how about stone spaces? So, well, let's just say what's stone duality? So stone duality establishes an equivalence between the category of Boolean algebras and homomorphisms, so things preserving that structure, is dually equivalent to the category of stone spaces and continuous maps. Okay, so what's a stone space? Let's find out. Stone space, what's that? So it's a compact Hausdorff zero-dimensional topological space. So what's zero-dimensional? It means it's got a basis of closed and open sets. Okay? So another way of saying that is that it's totally disconnected. Okay? Alright. So that's stone duality. It's due to stone. But it's also, so Stone didn't have the notion of a category when he proved it back in the 30s. And so I guess at some point people realised that it was an equivalence of categories. I guess in particular one place you can find this written down is in the thesis of Doctor. Okay? Okay, so that's Boolean algebras. So, if you actually look at Stone's paper, he doesn't actually prove the duality for Boolean algebras, he proves the duality for something else. Now, these somethings are something that he called generalized Boolean algebras, which is a name which is so bad that you can't help but feel he introduced it in the hope that someone then later renamed them after him. Now, of course, he rather torpedoed this because he then went on to prove Stone duality, which was a much more interesting result. And so that became named after him. And so we're stuck with the name generalized Boolean algebra, it seems. However, I'm not going to use it. I'm going to use a different name. I'm going to talk about Boolean semilattices. So this is a sort of, there's a respectable tradition, I guess, coming from domain theory, that if you take some ordered structure and you kind of remove the top element, then you suddenly refer to it as semilattice. Okay, so what's a Boolean semilattice? Well, again, I can describe it just like I described a Boolean algebra in two different ways. Okay? So on the one hand, it's the complete theory of some operations, and again, these can be operations on a power set lattice. So we've got intersection join, we've got 0, and we've got set difference. Okay? And so we just look at those operations on power set lattices. Okay, so you see in particular that we don't have a top element necessarily, although power set lattices of course do have a top element. That's not really part of our theory. Okay? So there's actually a sort of full sub-theory of the theory of Boolean algebras. The full sub-theory generated by these operations here. Okay? Alright. So that's one description. And there's another description, which again is to describe it as an endomorphism theory. So what endomorphism theory is it? It's the endomorphism theory of the pointed set, set 0, 1, comma 0. And so again, you can say what that means. This is that n-ary Boolean semilattice operations correspond to 0 preserving maps from 2 to the n into 2. Okay? So particularly you can see that the constant 0 is a 0 preserving map, but the constant 1 is not a 0 preserving map, and that's why there's not a 1. Okay? But you can see that set difference preserves, set difference preserves 0, and so that's in there, and so on. Okay? Okay. Now, as I said, hang on, let me do something here. Yeah. Okay, good. So, as I said, Stone didn't actually prove Stone duality originally for Boolean algebras. He proved it for these semilattices. And so, I'm going to state the version which is sort of closest to his formulation first, and then I'm going to explain why it's not the sort of the nicest version from a category theoretic perspective. Okay, so there's actually two categories of Boolean semilattices I want to consider. So we have BSL, which is what you expect. It's Boolean semilattices and homomorphisms. There's another category called BSL proper, and this is the category of Boolean semilattices and proper homomorphisms. Okay, so what's a proper homomorphism? I'm not going to tell you. So it's kind of not important because, as I will suggest in a moment, we don't want to think about the proper homomorphisms really. Okay, but they're important if I want to state the sort of usual formulation of Stone duality for these Boolean semilattices. Okay, so the typical formulation, and again this is due to Doctor, is that the category of Boolean semilattices and proper morphisms is dually equivalent to the category of, so we're going to call them Boolean spaces and proper continuous maps. Okay, so you'll notice there's another word here called proper. This is a different proper, but it's a proper that's standard from topology. It means that the inverse image of a compact set is compact. Okay? Alright, so what's a Boolean space? Well, it's very similar to a stone space. So this is a locally compact Hausdorff zero-dimensional space. Okay? Alright. So there's some sort of awkwardness about this, right? I mean, there's this word proper, which I'm refusing to tell you what it means, and then there's word proper here. And the reason it's awkward is because this isn't just the category of homomorphisms for this structure. Okay, so you might say, well, can we do better? And the answer is yes. So let's look at the category of all Boolean semilattices. So this is dually equivalent to, well, the objects are going to be the same because the objects are the same on the other side. So I'm going to get Boolean spaces. But what I'm going to get are partial proper maps. Partial proper continuous maps. Okay, so we've got rid of the word proper on one side. You'll notice it's still there on the other side. And we've also introduced partiality, which may seem inconvenient. So the partiality is you have a function defined on an open subset of the domain. That's the kind of partiality we're talking about here. But we can make all of this awkwardness go away once and for all if we do the following. So BSL is duly equivalent to the category of pointed stone spaces. Okay, so how does this work? Well, it seems that I've somehow identified this category here with this category here. And that is indeed the case. If I have a Boolean space which is locally compact Hausdorff zero-dimensional, I can take the one-point compactification and that will give me a stone space. With a point, which is the point I just added, which I suppose you could call infinity. On the other hand, if I've got a pointed stone space, I can remove the unique point, well, not the unique point, I can remove the point I've selected, and the result will be a locally compact Hausdorff zero-dimensional space. And so that's the duality. And you can see, therefore, why you get partial proper maps, because if you have maps between pointed stone spaces, you can send things that aren't the point to the point. And so when you remove the point, you only get a partial map. And so in those terms, you can understand what the properness condition is now on the side of Boolean semilattices. It's exactly the condition that the corresponding map on pointed stone spaces not only preserves, but reflects the point. Okay?
The partial proper maps are actually defined on open subset?
Yeah.
Subspace? Okay.
Yeah. Okay. So that's section 1. Don't have any questions? Alright. So here's section 2. So section 2 is going to be section 1 categorically. Okay, so I suppose I should say here that kind of these things here were observed by Linton in 1970. Okay, so how do we get stone duality categorically? So if I were Tom Leinster, then I'd say that there's a machine which, when fed as input the two-element set, will return stone duality. So I'm going to describe that machine to you, and then we'll see that it not only gives us stone duality for Boolean algebras, but I can also get it for Boolean semilattices as well. So here's the idea. I'm going to start from any object V in a complete category, C. And I'm going to consider T, which is the endomorphism theory of the object V. So this is a finitary monad on set with Tn given by the set of maps in C from V to the n into V. Okay, so you could ask what the algebras are for this monad, and there are a bunch of algebras, but there's one particularly sort of glaringly obvious algebra, which is that the object V itself is an algebra for this monad in an internal sort of algebra for this monad in the category C itself. Okay? So V is an internal T algebra in V and C. Thank you. So we get a lifting so we can take the representable functor homing into C. So that's a functor which I am going to think of as a functor from C into set op. Okay, so that's C blank V. So that's going to lift through the category of genuine T algebras in set. Okay, and so you've got this lifting here, so which I'm going to call that L. Okay, so using, let's move this here. So using limits in C, we can construct a right adjoint R, which goes from T alg op into C. Okay, and so the idea is that this thing is going to take the free T algebra on one generator and it'll send that to V, and then, well, that tells us what it must do on co-products of algebras, right? It must send it to V to the n, and then everything's a co-equalizer of co-products. So that tells us how to define R everywhere. Okay? So what we have now is a little adjunction. So let's see what this gives us in our two examples that we've been looking at. So Boolean algebras first. So we're going to take C to be set, and we take V to be 2. So then, as I explained, the theory that I get, this endomorphism theory, is a theory of Boolean algebras. So T alg is the category of Boolean algebras. And so what's our adjunction? L left adjoint to R. Well, it's this. I've got BA op here. I've got set. I've got this right adjoint, which I can describe rather explicitly, right? This is actually just BA blank 2. And then this thing here is actually set blank 2. Okay, so that's the power set. And this thing down here is the ultra filters. This takes the Boolean algebra to its ultra filters. So what's an ultra filter to Boolean algebra? I guess Pino told us this already, but it's just a Boolean homomorphism from a Boolean algebra into 2. Okay? Okay, so that's the first example. So the second example, so far all we've done is construct an adjunction, but we'll see why we've constructed an adjunction shortly. So let's take C to be pointed sets, and we'll take V now to be the set 0, 1 pointed by 0. So now T alg is the category of Boolean semilattices, and all homomorphisms. There's no properness here. And our L left adjoint to R is the following. So here's a Boolean semilattice. I suppose there's an op here. So maybe I'll just describe what these functors do. So this top one here takes as pointed set x, comma x, and it sends it to all the homomorphisms into 2, which send the point to 0. Okay? And so what's that? That's the power set of x without x.
There should be a star as a set.
A star? Yeah, that's my point. It's called little x. Oh, here, yeah, I see. Thanks. So what does this one in the other direction do? Well, it takes a Boolean semilattice here, and it sends it to the set of all Boolean semilattice homomorphisms from B into 2, but it's got to have a point. And so what's the point? The point is just a zero map from B to 2. Okay? So for a Boolean algebra, these so-called ultrafilters correspond to subsets of the Boolean algebra, but they can't be empty because the top element has to get sent to the top element of 0, 1, which is 1. And so the equivalent thing, the ultrafilter in a Boolean algebra, always contain the top element. For Boolean semilattices, there is no top element, and there's nothing to preserve. And so it's perfectly valid to have one of these things being the zero homomorphism, which corresponds to an empty, an empty prime filter on a Boolean semilattice. Okay? Alright, and so you can see that this is actually the disparity when you get to stone duality. So in the sort of stone formulation, you omit that empty prime filter, and that gives you these Boolean locally compact spaces. But if you keep that empty prime filter in there, then you get a stone space with a point, which is this empty thing. Okay? Alright, so back to the general case. So we can consider the monad, which I'm going to call S, on the category C. So remember the picture that we had. We've got C here. We've got T alg op, which was the endomorphism theory of this object V in C, and we've got an adjunction like this, okay, given by a sort of homing into V in both directions. So we can consider the monad on C induced by this adjunction. Induced by this thing here, I suppose. And, well, when we do that, we can look at its algebras. So it's Heidelberg-Moore algebras. And the comparison functor, which looks like this. So I've got T alg op, and here I'm going into. So this sits over C via this right adjoint R. Over here I've got the Eilenberg-Moore algebras for the monad S, and so here's the forgettable functor for that, and I get this comparison functor, which you always have just by sort of basic Cassidy theory. Okay, so if we're lucky, then K is full and faithful, and so we get an equivalence. Between T alg of and the essential image of this comparison functor K. Okay? Alright, so let's see what this does for our examples. So from this adjunction between Boolean algebras and sets, what do we get? Well, we get a monad on set, where I take a set, I send it to its power set, and then I take the ultrafilters of that Boolean algebra. And so that's what you would think of as just an ultrafilter on the set. And so we get the so-called ultrafilter monad, which is usually called beta. So how does it work? So beta of a set X is the set of all U contained in the power set of X, such that U is an ultrafilter on X. So Manes showed that beta algebras are isomorphic, in fact, to compact Hausdorff spaces. And so we have what? So I've got BA here. And what I'm mapping into now is actually the category of compact Hausdorff spaces. This is all over set. And so this is some lifting of BA blank 2 through the category of compact Hausdorff spaces. And what does it do? So this thing here sends B to its set of ultrafilters with a suitable topology. And what's that suitable topology? It's the one that Stone wrote down. Okay? So in fact, this functor is full and faithful, and so BA op is equivalent to the essential image of this K, and this is the category of stone spaces. Okay, so there we go, there's stone duality. So let's just quickly look at the other example we had, which is these Boolean semi-lattices. So from Boolean semi-lattices we have this adjunction with pointed sets. So we induce the pointed ultrafilter monad on set star. So I've got a beta star. So what does beta star do? I mean, it's not very exciting. So beta star applied to a pointed set x, x is beta x, and now I'm going to give it a point. So what I do is I just use the unit of the monad to embed x into beta x. So that's the principal ultrafilter at little x. Okay? These algebras are pointed stone spaces. So pointed compact Hausdorff spaces. So then we sort of continue as before to get that Boolean semi-lattices op is equivalent to the category of pointed stone spaces. Okay, right. So just one final thing before we get on to what I actually said I'd talk about. So that is how to show that this functor K is fully faithful. So how to show, so in the general case, that K is full and faithful. Okay, so one approach is just to try and do it by hand. And if you do that, you have a terrible time. So some machinery is in order. I mean, it's not that terrible a time, but it's not great. So what does it say to say that K is full and faithful? So remember, we've got a monad, we've got a junction. We're looking at the category of algebras induced by that junction and the comparison functor. And we're asking when that's full and faithful. So it says that L left adjoint R is of descent type. Okay. In other words, it says that the co-unit maps okay, I'm going to put this in quotes. They are the co-unit maps, but this is a contravariant adjunction, so it kind of appears to have two units. Okay, so it's mapped from B to LRB in T-alg. Okay, so that's the co-unit in T-alg, but it seems less confusing to see it as a map in T-alg. And so the condition is that those are regular monods. Okay, so again, you can try and prove directly that this is true. So in the category of Boolean algebras, this is embedding of a Boolean algebra into its canonical extension. So Stone's representation theorem says that map's a mono, but you want to show it's a regular mono, and so unfortunately that puts you in for a bunch more pain, basically. So you want to avoid doing that. And so, rather than do so, I'm going to state a little lemma. So this is a lemma that my student came up with. So Ellie came up with this. It's quite a nice little lemma, I think. I told this to Walter and he said it seemed good. Well, he said it seemed fine. But I was just asking him if it seemed correct or like known. And I think the conclusion was that it may or may not be known, but it's kind of a respectable result. Okay, so I got this category C, which has kernel pairs and co-equalizers of such. And I've got this adjunction, and I'm going to suppose that R is conservative. So that's necessary for it to be a descent type. The second condition is not necessary, but it's quite convenient. So I'm just going to ask that it sends regular FEs to FEs. Okay, so that will do it. And these conditions are quite easy to check in Boolean algebras, and so this gives you a way to establish this full fidelity without doing too much work. I should say that normally you would establish these kinds of properties using stone duality, which of course we can't do here, not sort of legitimately, but we can avoid this perfectly well by instead proving them directly, okay? And proving these facts about the Boolean algebra set adjunction is much easier than trying to show that this map is a regular monad, just by brute force.
So is the conclusion of the lemma that the adjunction is of descent type?
Oh yeah, I suppose it needs a conclusion, doesn't it? Then of descent type. Thank you. Very good. Okay, so I've told you now about stone duality for ordinary Boolean algebras and these slight variants. So let's now talk about skew Boolean algebras. So we're going to talk about skew Boolean algebras and their stone duality.
Richard?
Yes?
So here in the lemma you have kernel pairs and co-equalizers of
Kernel.
subs.
Yeah.
But your original C was just finally complete.
It was complete, so I guess I'm probably need to add this in.
Okay.
I agree. So, okay, so that's if I want to show that this is of a descent type, which it may or may not be, in general. If it's not a descent type, then it will still have a left adjoint, and I can still look at the fixed points of that adjunction, and so I'll still get some kind of duality. So the full faithfulness here is just sort of almost a convenience, because then it makes it very easy to identify the equivalence that's hidden within this adjunction.
So just one comment on
Yep.
these two conditions. So the first just says equivalently that the co-unit is an extremal atom.
Yep.
So what the second does is it closes this tiny gap between extremal and regular.
That's right. That's right. But it's a real gap. So in the categories we're going to talk about now, the regular epis and the strong epis definitely do not coincide. Okay, good. So skew Boolean algebras. So who knows what a skew Boolean algebra is? Amazing. That's good. So it's actually something fairly straightforward. So if x and y are sets, then I can look at the set of partial functions from x to y, and that supports these operations. So what should I call these operations? How about 0, meet, join, and set difference. Okay. So what do these operations look like? So 0 is undefined everywhere. That's a perfectly good partial function. So I've got two partial functions, f and g, and f intersect g is going to be given by f restricted to the domain of f intersect the domain of g. Okay, so I just take f and restrict it to the places where g is defined. F set minus g is quite similar. I'm going to take f and I'm going to restrict it to the places where f is defined but g is not defined. Okay? Alright, and so then the final one is a bit more fun. So f join g. Okay, so you might think I'm going to write f restricted to the domain of f join the domain of g, but that's obviously nonsense. But I'm going to write something that's sort of similar to that. So I'm going to say that it's going to be f on the domain of f, and it can be equal to g on the domain of g without the domain of f, and it's going to be undefined elsewhere. Okay? So I take a join of these functions. They may not agree where they overlap, and on the overlap I'm just going to ignore what g does and just take f. Okay? Alright, so this I think is sort of reasonably natural kind of thing to do. And so what I can say now is that right skew Boolean algebras are the complete theory of these operations on sets of the form partial function x, y for all x and y. So I look at all the equations that hold in all of these algebras of partial functions, and those are the axioms for skew Boolean algebras. Okay? So in particular, that means if you want to work out if some equality is true in this theory, I just see if it's true in one of these partial function algebras, and then I'm done. Okay.
In all of them.
I mean, in a generic one, I guess.
Okay.
If you don't know anything about it, it's going to be generic, right? But yeah, in all of them. So what's the stone duality for this? Okay, so you notice there's the word right written down there. So why did I write the word right? Well, because you can see there's a sort of asymmetry to this definition, right? I've preferred F here on the left for this. Oh no, I've done something terribly wrong. So actually, what I've done is given you an incorrect definition, right? So what I'm going to do is give you a correct definition there. So, okay, I'm going to prefer G on this side. Okay. So that's better, right? Okay, right. So for the and, I prefer the left operand. For the or, I prefer the right operand. Okay. So that's sort of what you might expect from De Morgan duality or something, right? You probably want to reverse the order or something like that. So anyway, I mean, these obviously aren't De Morgan dual operations, but oh well. So there's no duality for these things. So anyway, right skew Boolean algebras, as I was saying. Blimey, okay. Let me try and do the sentences one at a time. So these operations are the operations for a right skew Boolean algebra. If I reverse the chirality of everything, I get left skew Boolean algebras. And that's all I want to say. But we're going to deal with these so-called right ones. Okay, so what's the stone duality for these things? So this is quite cute. And it's due to Kotia Seva. And so it says that the category of skew Boolean algebras, so right skew Boolean algebras and homomorphisms, is dually equivalent to a certain category. It's a category of sheaves on pointed stone spaces. Okay, so what does that mean? Well, I'll tell you what the objects and the morphisms are. So the objects look like this. So it's X and a point, as pointed stone space, or I'm going to call the point infinity. And then I'm going to take a local homeomorphism and then there's a sort of global support condition which says that P inverse of X is not equal to 0, well, almost everywhere except at infinity. So at infinity the fibre should be empty and everywhere else the fibre should be non-empty. So those are the objects. So what are the maps? So here's an object y1 down to x1, and here's another object y2 down to x2. And you might wonder why I'm doing this, because surely you know what the maps are. And if you know what the maps are, then you're probably wrong, because they're this. Okay, so I give an F down here, and then a G up here, out the pullback. Okay? Alright, so if you think of the codomain fibration of set, then this is like you take the opposite fibration of that. Okay? And I should say that these maps will automatically preserve the base point. Okay? Just because of how empty fibers work. You can't map into an empty set except from something empty. Okay, good. So, on to the last bit. So, what we want to do is do section 3 categorically. I mean, I should say this paper is already very categorical, so somehow that's a very unfair thing for me to say. What I mean, I'm going to do it in the style of section 2. Okay? So step 1. So remember, at some point you want to create an adjunction, which when I take the algebras will give us something like some kind of topological structure. Okay, so when I take the algebras for the induced monad, it will give me some kind of topological structure. And so probably what I should take for the category on which that monad is going to subsist is a detopologization of the category of these topological structures, which I know what they are. That is this stuff here, right? So let's detopologize this category of sheaves on stone space. So detopologize. So let's make a definition. So poly is the category with, so objects are functions y to x, and maps from y1 to x1 across to y2 to x2 are these funny pullbacky things. Okay, so what is this category? So it's equivalently, it's the category of polynomial endofunctors of set. Okay? And so you can interpret that however you like. You can interpret it in the sort of abstract sense, or you can just say that the things that are generated from finite limits, the identity, finite products, the identity of finite coproducts. Okay? Or arbitrary coproducts. And maybe arbitrary products as well. Okay, there we go. How about that? Okay, so, it has lots of other characterizations. It's the free distributive category on 1, and so on, but I won't go on. But I'm also going to find something a bit related, which I'm going to call poly star. So this can be a full subcategory on those y to x, such that there exists a unique x in x whose fibre is empty. Okay? So that's the same condition we saw before with the Kudret-Sierra result. So if I look at this tells me that I'm looking at polynomials of the form 1 plus x times px. Okay? Alright, so those are kind of fairly noble and well thought of polynomials, so that seems quite good, right? Okay, so here is an amazing fact now. So I can look at the endomorphism theory of the subobject classifier, okay, which is also the polynomial 1 plus x. And this is the theory of right skew Boolean algebras. Okay, so at this point we're extremely happy because we can apply the material of section 2 and see what happens. So from this we get an adjunction. So here I've got poly. Alright, so there are a choice here, right? I can look in poly, or I can look in poly star, and I'm going to get the same endomorphism theory. So actually what I want to do is take, in fact, poly here. Maybe I'm going to put it over on the right. Poly star, sorry. And then over here I've got T alg op, which, as we ascertained, is SBA op, and so you get an adjunction like this. And that induces a monad over here. Okay? And a monad. So we might ask, what is this monad? So S is in fact element ultra sheaf monad. So let me describe what this does. So S, I have to apply it to a polynomial. So what's it going to do? Well, at the bottom it's just going to take the ultra filters. And then up here, what do? I'm going to take co-product over all ultra filters. And then basically, this is a family of sets Y, right? So I'm going to take the ultra product of the sets Y, I. Okay? And that's the phi. Okay, so, one way of thinking of this is that this is a sheaf on the discrete space X. We have the unit here of this monad, and I can pi this sheaf along here and produce a sheaf over here. Okay? So as you can see from what I just said, this can actually be a local homeomorphism when I endow these things with topologies. And the reason for this is in fact, Kennison showed that the algebras for S are sheaves on compact Hausdorff spaces. Okay? And so we get our comparison function now, and that's going to go from skew Boolean algebras off over into this category of S algebras, and that's the category of sheaves on compact Hausdorff spaces with these funny maps, the sort of backwards pointing maps. But remember, we were doing all of this. On poly star, so there's a star here. Okay, so you might wonder why I put this star here and so forth. So what's actually true is if I don't have the star here, the monad I get isn't quite the ultra sheaf monad. It's kind of the composite of the ultra sheaf monad on poly, which is where it's normally defined, with the reflector into this subcategory here. Okay? So I might as well just work with this subcategory to start with, and then everything becomes somehow more appealing. Okay, good. So there we do it. There we go. So we've got this functor, and we can now check conditions of Ellie's lemma to see that K is in fact full and faithful. Okay, so that's a bit of work, but it's not too bad actually. And finally, you just by hand characterize the image, a central image of K, as sheaves on stone spaces. Okay? Alright, and so that's kind of it. I see I've got a few minutes left, so maybe I'll make some little comments about this. So, right, so maybe I didn't actually explain what this duality means, like what's going on. So kind of the idea is that a skew Boolean algebra has this non-commutative structure, which is a bit like a Boolean algebra. If you force that operation to be commutative, it actually becomes not a Boolean algebra, it becomes a Boolean semilattice. Okay? And so that's what's happening here. If I've got a skew Boolean algebra, I'm going to produce over here, I'm going to lift through this category of sheaves on stone spaces, and the stone space at the bottom is actually just the pointed stone space associated to this quotient. Okay? So Clemens has done a bunch of work on these things, and that's sort of the starting point for the way that he and Maigurka do this. Okay, so in fact, maybe that's a good sort of final comments. Maybe it's good to end with a question, get in ahead of the audience. So, can we do, in a similar way, the duality between so-called skew distributive lattices and sheaves on spectral spaces? Okay? I suspect this is the wrong thing to say. I should probably say sheaves on priestly spaces, I think. So, why do I say that? So Ellie did this for just plain distributive lattices, so you can do this. In that situation, you start with the complete theory of the poset 2, okay, which is the theory of distributive lattices. You get an adjunction then between posets and distributive lattices. And the induced monad on posets is the monad for ordered compact Hausdorff spaces. Okay, so when I say an ordered compact Hausdorff space, I mean one in which the order is a closed relation. Okay? Alright, and then you do the same thing again, and the image of the comparison function in that case would be exactly the priestly spaces. Okay, so a priestly space is a stone space satisfying an extra order property. What is a stone space with an order, and then there's some further disconnectedness of the stone space with respect to this order. Okay? Alright, and so quite reasonably you might think, well, there's a notion of skew distributive lattice, which I didn't tell you about, but it basically drops the kind of the set difference from the axiomatization that you saw for the skew Boolean algebras. And so you can see if applying the same kind of machinery would yield sheaves on Priestley spaces. But I guess you first have to decide what to replace the category of polynomials with. I suppose it should be something involving like kind of polynomials on posets or something like that. So maybe like a poset and then a discrete fibration of posets over it or something like that. There's some nice exponential maps in a category of posets, so that seems kind of reasonable. Okay. As you can see, I've run out of material and now I'm kind of waffling. But that's good, right? No one's ever unhappy when someone finishes early, so I think I'll do just that. Thank you.
Okay, more questions?
Thank you very much, Richard. This is something I was expecting. Thank you. You come up with the various examples you've presented with a category on the other side, which consists of topological spaces or something which has to do with topologies. Do you see any reason why topologies appear on the other side from the analysis you perform?
So it's okay. So there are various answers to this. So one is that I think Isbell did. So Isbell has a paper in the sort of mid-60s or something where he explains various kinds of dualities, and I think in there's some statement to the. So I mean, okay. Of course, I'm not the first person, and Ellie and I are not the first people to try and come up with an abstract framework like this, and so Linton did it and Isbell did it before that, and in particular Isbell has some argument as to why these things should have induced topologies on this other side. So a more kind of direct answer, I suppose, would be that, so why do you get topologies? Oh no, I've forgotten what the direct answer was, that's a shame. Maybe I'll remember it in a minute. Maybe someone else should ask me a question, then if I remember, I'll tell you.
John?
It's a silly question, probably.
Yeah.
What if you replace 2 by 3?
Oh, right, okay, that's a great question. So, 3 in set.
Yeah.
I don't know what the complete theory of 3 is. So, among the sub-theories of 3 are all sorts of things. So, skew Boolean algebras are a sub-theory of 3. They have a faithful 3-element model. There's all sorts of things in there. Like, with a 2-element set, people have a very good understanding of what the sub-theories of Boolean algebras are. So Boolean algebras is the largest theory with a faithful 2-element model. And so all the sub-theories of that are kind of understood. That's called post lattice. But for 3 elements, very little is known, I believe. And in particular, I don't really know what the complete theory of 3 is.
Or the endomorphism.
Yeah, exactly. I don't know what that is.
Okay.
David?
Thanks for this great talk. 1 plus x, you can see as coalgebras as partial dynamical systems, let's say, on a set. Is there any connection between this story and the sort of dynamical picture looking at coalgebras of polynomial functors?
So maybe I'll interpret your question in a way that I can say something. So what you might think about is the fact that poly is a monoidal category. Okay? And that monoidal structure is somehow very important. So I think what's true... So, okay, the subobject classifier is a monoid for the substitution tensor product. Okay? So that means that if you hom into it from a co-monoid, then you get a monoid. Okay? So, what's a co-monoid in polynomials? It's a small category. So that means if you take a small category, then you can sort of hom into 1 down to 2, and you'll get not just a set now, but a monoid. And so what's that monoid? It's something that Marcelo Aguiar study, which is this monoid of admissible sections. So basically for each object you choose a map out of that object, and then they form a nice monoid. Okay? So in this situation, if I start with a small category, then I can produce something that's not just a skew Boolean algebra, but also has a monoid structure. Okay? So these are and then if you ask those to be compatible, you get what's called a Boolean right restriction monoid. So they're a generalization of a Boolean inverse semigroup. And so I think by sort of enhancing things in this way, you can reconstruct something else that's also called non-commutative Stern duality, which is something that Mark Lawson did, which is the duality between Boolean right. Well, he did Boolean inverse semigroups, but there's a more general thing, which is, I guess Robin and I did, which is Boolean right restriction monoids are dual to source-Étale categories with base space, Stone space. That's probably much more information than you wanted. Yeah.
Can you try to do something like the duality between sister algebras and other compact spaces, locally compact spaces, similar to like using this machinery?
That's a great question. Haven't looked at it, but I mean, there's sort of interesting things, I think. I sort of feel vaguely hopeful. So like Bart Jacobs has a bunch of results on kind of these sort of more probabilistic and analytic junctions from the perspective of dualities. So I suspect if you sort of dug into that, you might be able to cook something up. Yeah.
So, from the point of non-commutative geometry,
Mm-hmm.
a non-commutative Boolean algebra would rather be an orthomodular pose.
Okay.
Is there any way how you can look at those objects via this machine?
So orthomodular lattices are not variety, I think. Are they a quasi-variety? Or are they variety?
I'm not sure.
Does anyone know? Oh dear, no one in the room knows. I have a sort of vague feeling there might be a quasi-variety. So I guess this is something that Ellie's working on, which is sort of where on one side you don't have a full variety, you have a quasi-variety. So the point is, if I've got a variety, then, so like in Boolean algebras, 2 is a cogenerator, right? So if you had a variety where you didn't have a nice cogenerator like that, you could violently force it to have a cogenerator by looking at the quasi-variety generated by some object. And so in other cases you need to do that. So perhaps there's a way of doing this for orthomodular lattices. You can sort of, there's a characterization of them as kind of things that admit monomorphism into blah blah blah. And you could then sort of adapt these kinds of arguments and get something together. But yeah, that's kind of what Ellie's doing for that thesis.
Okay, we better leave it there. Let's thank Richard again.